Hello folks, welcome to a presentation on FIR filters. FIR filters stands for finite impulse response filters. In these kind of filters, what you will observe is that you have only zeros. There are some properties of FIR filters. The FIR filters are always stable. FIR filters with exactly linear phase can easily be designed. FIR filters can be realized in both recursive and non-recursive structures. FIR filters are free from limit cycle oscillations when implemented on finite word length system. Excellent design methods are available for the design of FIR filters. There are some disadvantages of FIR filters. Firstly, the implementation of narrow transition band FIR filters are very costly as it requires considerably more arithmetic operations and hardware components such as multipliers, adders and delay elements. Memory requirements and execution time are also very high. So we look at one of the first methods of making a FIR filter, which is called as the Fourier series method. Generally, when we discuss discrete time Fourier transform, we discussed an equation where hd of e raised to power j omega is equal to summation n is equal to minus infinity to infinity hd of n e raised to power minus j omega n. From here, if we take an inverse discrete time Fourier transform, we got hd of n is equal to 1 by 2 pi integral minus pi to pi hd of e raised to power j omega e raised to power j omega n d omega. Remember, hd of e raised to power j omega is nothing but the frequency response of the filter. And now what we need to do is, if we design a filter like this, you can get infinite number of coefficients. So what we do is we truncate the infinite number of coefficients to a finite number of coefficients which are given by hd of n for absolute value of n is less than equal to n minus 1 by 2. Let us take an example. Let us say that hd of e raised to power j omega is equal to 1 for minus pi by 2 is less than equal to omega is less than equal to pi by 2, and it is equal to 0 for pi by 2 is less than equal to absolute value of omega is less than pi. Find the values of h of n for n is equal to 11. So what we see is hd of e raised to power j omega is equal to 1 for minus pi by 2 is less than equal to omega is less than equal to pi by 2, and it is equal to 0 for pi by 2 is less than equal to absolute value of omega is less than equal to pi. If you really show the frequency response plot, you have a plot going from minus pi to pi, and we have hd of e raised to power j omega is equal to 1 only from minus pi by 2 to pi by 2. Using this particular formula where hd of n is equal to 1 by 2 pi from going from integral minus pi to pi hd of e raised to power j omega e raised to power j omega n d omega, I can put 1 by 2 pi integral going from minus pi by 2 to pi by 2 e raised to power j omega n d omega. Remember, the integral of e raised to power j omega n is e raised to power j omega n by jn. So I get 1 by 2 pi jn e raised to power j omega n going from minus pi by 2 to pi by 2, which is 1 upon pi n into 2j e raised to power j pi n by 2 minus e raised to power minus j pi n by 2. If I take 2j common on the denominator, I can write this as sine of pi by 2n by pi n, where minus infinity is less than n is less than equal to infinity. This particularly shows that we can have infinite number of coefficients for hd of n, but according to the problem we need to limit it for n is equal to 11. So what we do is we take h of 0, h of 1 and h of minus 1, h of 2 and h of minus 2, h of 3 and h of minus 3, h of 4 and h of minus 4, h of 5 and h of minus 5. See that these filter coefficients are symmetrical. So what you get is you get values of 0, minus 0.1060, 0.06366 as the corresponding values. See, whenever we have filter coefficients on the left hand side of the origin, this is a non-causal filter, so we can obtain a causal filter by shifting all these responses to the right. So what we can get is h of 0 and h of 10 to be 0.06366, h of 1 and h of 9 to be 0, h of 2 and h of 8 to be minus 0.1060, 106, h of 3 and h of 7 to be 0, h of 4 and h of 6 to be 0.3183, and h of 5 to be 0.5. Take another example where we have a band pass filter, and what we have is hd of e raised to power j omega is equal to 1 for pi by 4 is less than equal to absolute value of omega is less than equal to 3 pi by 4, and it is equal to 0 otherwise. The best thing to realize this kind of a thing is to be able to draw a frequency chart. So in the frequency chart we have omega where it goes from minus pi to pi, but hd of e raised to power j omega is 1 only from minus 3 pi by 4 to minus pi by 4 and from pi by 4 to 3 pi by 4. Now again using the formula hd of n is equal to 1 by 2 pi integral minus pi to pi hd of e raised to power j omega e raised to power j omega n. I have 1 by 2 pi integral minus 3 pi by 4 to minus pi by 4 e raised to power j omega n d omega plus integral pi by 4 to 3 pi by 4 e raised to power j omega n d omega, which is equal to 1 upon 2 pi j n in brackets e raised to power minus j pi n by 4 minus e raised to power minus j 3 pi n by 4 plus e raised to power j 3 pi n by 4 minus e raised to power j pi n by 4, which can be given as equal to 1 by pi n sine of 3 pi n by 4 minus sine of pi n by 4, when minus infinity is less than equal to n is less than equal to infinity. So now what we do is, this is actually an infinite number of impulse samples. We truncate it to 11 samples, so we get h of n is equal to hd of n, where absolute value of n is less than equal to 5. Here again you can obtain h of 0, h of 1 and h of minus 1 to be 0, h of 2 and h of minus 2 to be minus 0.3183, h of 3 and h of minus 3 to be 0, h of 4 and h of minus 4 to be 0, and h of 5 and h of minus 5 to be 0. Thus you have the required filter coefficients. See, whenever we are making FIR filters using Fourier series method, what we are doing is we are truncating the response of the filter to a finite value. Actually the number of filter coefficients is infinite. Whenever you truncate the filter coefficients by some kind of a window, which in this case happens to be a rectangular window, you get problems in the passband and stopband of the filter due to what is called as Gibbs phenomena. So for this case, I am showing a rectangular windowing technique, and whenever you are designing a filter with the windows, what you should notice is the central lobe of the frequency response of the window should contain the most of the energy and should be narrow. The highest side lobe level of the frequency response should be small. The side lobe levels of the frequency should decrease in energy as omega tends to pi. So given here I am showing a rectangular window WRN is equal to 1 for minus n minus 1 by 2 is less than equal to n is less than n minus 1 by 2 or 0 otherwise. And I am showing the amplitude and frequency response of this filter. This shows the energy suppression content of the window. Likewise, I am showing a triangular and a Bartlett window, which is WTN is equal to 1 minus 2 absolute value of n by n minus 1 for minus n minus 1 by 2 is less than n is less than equal to n minus 1 by 2. Here again I am showing the amplitude response for the normalized frequency and the frequency suppression characteristics of the window. Likewise, we have a raised cosine window where W alpha n is equal to alpha plus 1 minus alpha into cos of 2 pi n by n minus 1 for minus n minus 1 by 2 is less than n is less than n minus 1 by 2. The next one is a Hanning window where WH of n is equal to 0.5 plus 0.5 cos of 2 pi n by n minus 1 for minus n minus 1 by 2 is less than equal to n is less than equal to n minus 1 by 2, and it is equal to 0 otherwise. Here again we are showing the normalized frequency response as well as the frequency suppression characteristics of a Hanning window. And next one is the Blackman window where W of n is equal to 0.42 plus 0.5 cos of 2 pi n by n minus 1 plus 0.08 cos of 4 pi n by n minus 1 by 2 for minus n minus 1 by 2 is less than equal to n is less than n minus 1 by 2 and it is 0 otherwise. Here again we are showing the normalized frequency response as well as the frequency suppression characteristic. Now let us take another example where what we need to do is design a high pass filter with a frequency response ht of e raised to power j omega is equal to 1 for pi by 4 is less than equal to omega is less than pi, and it is equal to 0 for absolute value of omega is less than equal to pi by 4. Find the values of h of n for n is equal to 11 using Hanning window and Hamming window. From the given characteristic, it is always convenient to draw a frequency response diagram which goes from minus pi to pi. So here we are going from minus pi to minus pi by 4 and we are going from pi by 4 to pi. Again using the formula hd of n is equal to 1 by 2 pi integral minus pi to pi hd e raised to power j omega e raised to power j omega n d omega. This is equal to 1 by 2 pi integral from minus pi to minus pi by 4 e raised to power j omega n d omega plus integral pi by 4 to pi e raised to power j omega n d omega. I can write this as 1 upon 2 pi jn in brackets e raised to power j omega n going from minus pi to minus pi by 4 and e raised to power j omega n going from pi by 4 to pi. Eventually I can solve the total equation to get 1 by pi n sin pi n minus sin pi by 4n. Truncating hd of n to 11 samples where we get hd of n for absolute value of n less than equal to 5. We can actually get h of 0 and h of 1 and h of minus 1 to be minus 0.225, h of 2 and h of minus 2 to be minus 0.159, h of 3 and h of minus 3 to be minus 0.075, h of 4 and h of minus 4 to be 0, h of 5 and h of minus 5 to be 0.045. Now what we need to do is take the equation for a Hanning window. So WH of n is equal to 0.5 plus 0.5 cos of 2 pi n by n minus 1 for minus n minus 1 by 2 is less than equal to n is less than equal to n minus 1 by 2 otherwise. So what you do is you find WH of n for n is equal to 0, WH of n for 1 and minus 1 which comes out to be 0.9045, WH of n for 2 and WH of n of minus 2 which comes out to be 0.655, WH of n of 3 and WHN of minus 3 to be 0.345, WHN of 4 and WHN of minus 4 to be 0.0945, WHN of 5 and WHN of minus 5 to be 0. It is not enough to calculate these coefficients. Now to suppress the ripples in the passband and in the stop band because of Gibbs phenomena, you need to multiply h of n with hd of n into wh of n. So you need to multiply the corresponding coefficients with that of the window coefficients and then find the order of the filter. Likewise, take another example where hd of e raised to power j omega is equal to e raised to power minus j 3 omega going from minus pi by 4 is less than equal to omega is less than pi by 4 and it is equal to 0 when pi by 4 is less than equal to absolute value of omega is less than pi. Again use the formula hd of n is equal to 1 by 2 pi going from minus pi by 4 to pi by 4 e raised to power minus j 3 omega e raised to power j omega n d omega which is equal to 1 by 2 pi integral minus pi by 4 to pi by 4 e raised to power j n minus 3 omega d omega to get sin pi by 4 n minus 3 by pi n minus 3. Again here you can get the coefficients of the Hamming window or the Hanning window. The next one which we consider is the frequency sampling method of designing FIR filters. In this method, given the frequency response, what we do is we sample the frequency response to get h of 0, h of 1, h of 2, h of 3, h of 4, h of 5, h of 6, h of 7, h of 8 and h of 9. And then what we do is From these sampled values, we take inverse discrete Fourier transform